Okay, so here's 2.8, graphing linear inequalities. We're also going to do absolute value inequalities. So here are some guidelines. You've got to graph the line represented by the inequality, and that's going to be called your boundary. So you'll have an inequality here. Then you have to shade the graph with the solutions. So this is going to represent all of your solutions. You're not going to have just a line, or you're just not going to have just a number. Then testing points is going to give you an exact idea of exactly where your solutions are going to be. If you have slope-intercept form, you can kind of say, oh, here I have a greater than, so I can go above my y-intercept, or if you have less than, you can go below your y-intercept and have a sense of above and below your line. Sometimes it's a little tricky for somebody, so if you have a testing your point, you know exactly where you were supposed to shade. You can read through that example if you pause the video. So let's try this one. We're going to graph x plus 4y greater than 2. And we have to decide whether we have a dashed or solid boundary. And here we've solved for the x-intercept and the y-intercept and come out with 2, 0, 0, 1/2 to get our line. And here's our line. And then here is testing our point. The easiest point to test is 0, 0. As long as your line does not pass through 0, 0, then you can test that point. You do not want to test a point that would be on your line. So I would not want to test the point right here, 2, 0, because it would not really give me a good answer. Whether we're going to shade above this line or below this line. But testing point to one side or the other of the line does tell you whether you are going to shade either way. And 0, 0 is so easy because when you multiply by 0, then it's super easy. When I plug that in, I've got a 0 x value, I've got a 0 y value. X is 0, 4 times 0. All this side comes out to 0. And so I get 0 is greater than 2, pardon my writing. And this is 0 greater than 2. Well, 0 is not greater than 2. That gives you false. And so here's where 0, 0 is. So this side is false. That's the side where 0, 0 is. So that side of the line comes out to false where your point was tested. So you would shade the other side of the line. If this side is false, this side must be your true side. That's where your solutions would lie. So if you want to see another line done, let me go back here. The question was whether it was dashed or solid. Dashed would be, or dotted. Since we had just a greater than, we did not have an or equal to part. That means we have a dashed line. Here we changed or transformed this line to get slope-intercept form. So solved and got all y all by itself. So we had 1/2 x minus 2. So we could graph our y-intercept, go up 1/2 for our slope, and we've got our line graphed. And this boundary is solid because we have the or equal to part. We have a solid line. And we can go on and test our point. Plug in 0, 0. You see we've got 2 times 0 plus 4 greater than or equal to 0, which is our x value. That would leave us with 4 is greater than or equal to 0. That is true. 4 is greater than 0. And here's where 0, 0 is in relationship to the line. And when we tested it, this portion is true. So we can shade all of that portion. And that is where testing gives you beyond a shadow of a doubt what is true, what's not, where do we shade. Now when we have horizontal and vertical lines, how do we do our shading in that respect? Well, let's graph these two lines. Here's our horizontal line at our -5. Here's our vertical line at 2. We need to take a look at our inequalities and let's think about just what makes sense. Of course, I didn't make this. This should be a dotted vertical line. Okay, where are the y values? So here's all of your y values. Where are the y values less than or equal to 5? Would that be above 5 or would that be below 5? Well, that would be below 5, so we'll end up shading down here. Where are the x values greater than 2? Would that be along your x-axis to the right of 2 or to the left of 2? Well, that would be to the right of 2. So that is where our shading occurs for both of these inequalities. Now, since we have discussed absolute values and how we are supposed to graph those, then you know how to graph your functions. You will have your vertex forms. Then we need to shade, just like we have shaded with the lines. We can test the points. We do not have any doubt whatsoever. So we need to know whether we have a dashed or a solid boundary. Well, take a look at your inequality. That will definitely be dashed, dotted, however you want to think about it. Where is H and K? And what is our A value? A, remember, will tell you how wide or how thin this V, quote unquote, will be. All right, so we have a dotted boundary. Our H should be in here between our absolute value symbols. We don't have a plus or minus anything. Our H is 0. K, back here behind the absolute values, which is 3. So our vertex is 0, 3. That's where we'll begin the V. And our A is 2, which resides in front of your absolute value symbols. So we will be more steep on the sides of our V graph. So here's how our V looks. 0, 3, here's our vertex, and we up and over 2, more steep on our sides, so there's our V. Now let's test a point. We throw in 0, 0, Y value of 0, X value of 0, and then absolute value of that, and 2 is multiplying by this absolute value, so we get a 2 here essentially. So when we check that, we have 0 is greater than 3, absolutely false. Here's where we have tested that point. This area is false, so we will essentially be shading inside that V. And again, you would be graphing the same thing. We would get a dashed because we do not have an or equal to part. Our H is inside here, and remember, if you are questioning why this has an opposite sign, we take this portion, set it equal to 0, solve for X, we get opposite signs for H. There's no K back here, it's 0. So here's our vertex, negative 1, 0. We have a 3 for our A value. So here's our V, much more steep again. We begin at negative 1, 0. Let's test our point. We get 0 greater than 3, no way. So that's false, and once again we shade inside the V. Will we always be shading inside of our absolute value graph? No, we just happen to have graphed to where it was false outside. So there will be times where you shade out here. Just test your point if you doubt at all.